Yeah, thank you very much. Yeah, this is a talk which has two parts, actually. A first one where I briefly give an overview of my own research interests and then lead over to some notes on questions about meta-logics and logics and proofs of consistency. Which I have worked out recently. That's unpublished material. Therefore, I would have liked to really share this more closely with you also in discussions at the event. However, maybe there are some other opportunities that can lead to fruitful discussions. Maybe that's all already known to you. Maybe it's new. You have to tell me. Well, let's start with that presentation. Ute Schmidt gave already a wonderful introduction and overview on AI. For me, it's important that I clarify my own working definition of AI in such and related talks. For me, AI is a scientific discipline studying intelligent behavior in machines and reflecting on intelligent behavior in machines from different perspectives. We have seen the distinction in these two notions of weak AI and strong AI. I don't have to say much about that, but what I want to say is that for me, strong AI requires at least 5 different layers and maybe more in terms of what we heard also at the end of the talk in terms of going direction of consciousness, qualia, and so on. I don't include it here. But what, of course, is obvious that we need this kind of simple problem solving in the sense of weak AI, play Go, play chess, solve classification tasks, and so on. But then there comes the exploration and acting in unknown territory where you don't have seen examples before, but nevertheless need to act. Gives you another challenging point here. For me, it starts to get interesting when we talk about abstract and rational reasoning. So how can it be that a mathematician explores this wonderful new mathematical theory and describes it symbolically so that we can pass that knowledge on to a next generation, or a physicist who observes pattern in the worlds and describes them declaratively in a well-defined language that we can pass them on, for instance, at university in our lectures? How about self-reflection? How can machines detect own mistakes, suffer from inconsistency, from refuting oneself, and so on? And how about social interaction, the adjustment of personal goal and values to those of others, to a larger community, for example, to achieve a greater good? And you see, I think that the latter layers, in particular, this aspect of abstract rational reasoning, isn't really sufficiently addressed yet in the neural or deep learning setting. In some of these areas, you start exploring theories from nowhere without having ever seen an example before. You nevertheless start with a metaphysical theory, for example. I have developed over the years a wide range of different research interests and activities. Relevant for this presentation here is this here. So what got me intrinsically interested in the very beginning was the question about strong AI. Jörg Siegmann brought it up early in lectures in the early 90s already. Provocative statements like, we are now the generation, so the student sitting in the audience, the generation who would witness this rise of strong AI systems that can eventually reproduce themselves and get stronger and stronger. So we debated that early 90s in these lecture courses, and I was shocked by these statements, partly because of my background, but also partly because I didn't want it to be true that machines can reach eventually human-like performance in all respects. So I dived into that question. It was very interesting for me, and I dived into mathematics. For me, the challenge question was, can machines ever reach human-like performance in mathematical reasoning, in particular also about the exploration of new mathematical structures. On the other hand, I was early on confronted with that perspective of verification of machines. Udo also briefly mentioned that early on. So the idea that computer programs can eventually be fully verified. So you can get guarantees and verify these guarantees and have security. At that time, these two positions were for me not so conflicting, because AI at the time, in the context where I was growing up, was mainly rule-based AI. So what we nowadays wrongly call good old-fashioned AI. And so there was not this sheer discrepancy, which we nowadays have with moving to just neural network statistics and so on. The problem of verifiability is clearly there. that is what I'm interested in with my personal research in the group. And of course here, I think that we need an integration to solve that problem between symbolic and sub-symbolic methods. So to get this yin and yang picture to rotate. I developed myself kind of proposals and research in the direction of so-called ethical governors or legal ethical governors, where you, for instance, have the objective to control the suggested actions proposed by an AI reasoners, here depicted in yellow, and have them undergo an additional compliance check by a symbolic layer. Think about Kahneman's distinction of system 1 and system 2. So here you have a system 2 layer, a purely declarative one, symbolic logic, for instance, used in order to check compliance of suggested actions in a given application context with regards to these ethical legal constraints. That is a research direction I'm interested in. And that, of course, means that you're also interested in eventually the question of a potential alignment with the model against the declaratively stated top-down rules and regulations with legal ethical content. So that is a brief depiction of this interest, meaning that I'm interested in putting AI systems into a protective shelves in highly critical areas and developing potential solutions for that. But a natural question now is, and that leads me to the main content of that talk, is, well, if you want to declaratively describe in symbolic logic or in rule-based systems in general, legal and ethical content, then this is a non-trivial task. So logicians know that, for instance, a proper modeling of notions like obligation or permission and so on is a challenging task. And in the area of the ontic logics, you develop new logics every year at the conferences they are presented. So the solution to that in my group, and we have developed that now over the past decade, is a meta-logical approach called LogiKEy. It's a methodology and infrastructure to deal with many, many different object logics in a meta-logic. Meta-logic needs to be sufficiently expressive that you can, ideally in a very elegant way, embed or axiomatize, and I avoid axiomatization, you will see that later, very naturally embed other logical formalisms that are then capable of, for instance, giving you a suitable and appropriate modeling for challenging notions like obligation or permission. So that means I have here a layered architecture that starts with a meta-logic, and in that meta-logic, I claim I can model many, many different object logics I'm interested in, some of which might supposedly, or at the first glance, even be more expressive than the original starting point. They are not, but it looks like at the first glance. So we have done many experiments, for instance, in metaphysics, where I modeled based on a classical higher order logic as the starting point, something like an intentional higher order modal logic, and did experiments on the ontological argument for existence of God. Checked many different variants in this area of metaphysics. Many papers published about new results also that we found out, failures in publications by humans detected by that machinery and so on. We did experiments in higher order free logic and showed in the area of foundations of mathematics that you can well axiomatize category theory on top of that. We did experiments in direction of value-oriented legal reasoning and used here higher order modal logic of preferences as a starting point to model value-oriented legal theories, and then applied it to show that you can now have a value-based assessment of some prominent legal cases in the literature. So that gives you now a flavor of this negotiable aspect of the object logic layers. And that brings me now to the question for this talk here, namely the question of what happens actually if I now use that architecture to study higher order logic in higher order logic, and higher order logic in higher order logic in higher order logic, and so on and so on. So to get that to an infinite regress. Is that possible, and what comes out of that? So that is a different way of reflecting on logic in logic than what Gödel did with his Gödelization. We might discuss that later on. I show you now actually how simple and elegant that can be if you start with a very suitable logic setting for that at the meta level. And this allows you then to reflect on the reasoning principles of the upper layer, as I claim, at the lower layers. It allows you to dive into proofs of soundness and completeness and consistency for the lower layers at the upper layers. And no axioms are needed. It's just a very natural isomorphism between a metalogical, a suitable starting point, and natural fragments of that logic, as you will see in a second. It's actually quite simple and astonishing elegant. So that is what we are going to do. And before I dive into the concrete modeling, which can be shown on one slide, I have to say a bit about the meta logic, because you might not know about it. So unfortunately, we have to dive now a bit more into some formal content. Please forgive me about that. So the starting point for the meta logic I chose in my work is classical higher order logic, or also known as Church's type theory, Church simple type theory, because it's based on the simply typed lambda calculus introduced by Alonzo Church. It's a functional higher order logic, and a logic of functional terms. Some of these terms of Boolean type are then our formulas. It's an expressive and elegant and compositional formalism, and it's the logic that is actually underlying most modern proof assistants nowadays, or they go a bit further and eventually have richer type theories they consider. But it's not that in that area of proof assistance systems, people, for instance, work with first order logic and set theory, axiomatizations of set theory, as many people still do in many other areas. So higher order logic, very simple syntax. Let me quickly introduce that. Forgive me if I'm boring you, because you know that already from some introductory classes, but I have to set the stage here. So it's a simple notion of types we have. We have a base type O standing for the Booleans, and a base type I standing for arbitrary objects, individuals. You can add more of those kind of types, like the I type for other sorts of individuals, and then you get a kind of modeling of a sorting logic approach. And then the essential idea here is that you build up function types, arbitrarily many ones. So type I to O for predicates, type I to I for functions from objects to objects, and so on, and you can iterate that process. Then you come to the layer of the simply typed lambda calculus, and I need here simply typed lambda calculus with additional constant symbols. So we have constant symbols, all of them are typed. We have variable symbols, all of them carry type information, and we can build now lambda abstraction, introducing us, that is the idea, unnamed functions. So lambda abstraction as an abstraction, a building of a functional object. And then the counterpart to lambda abstraction, so the building of a functional object that abstracts over that argument x that might be in the body of S, is the application of functions to terms, application of S to T. And this is all governed then by the rules of beta-eta reduction. So lambda conversion rules are implicitly assumed here in the background that actually give us a meaning to application here, for example. You see that here. You have probably all heard about that in your introductory classes. So now from simple type theory, or the simply typed lambda calculus, you can get to a higher order logic simply by adding some particular kind of constant symbols to the signature, which get a predefined meaning. For instance, the negation symbol is a typed symbol from the Boolean type to the Boolean type, and it's just flipping truth values. So the only assumption in the logic here is that the type O has just these two objects, true and false. That is a background assumption in logic. And then I built in a fixed meaning for the negation constant, and also a fixed meaning, the obvious one for disjunction, and this universal quantification symbol pi. In this framework, we can really introduce quantification by just the constant symbol, like the other connectives, and then viewing for all xs as just an abbreviation of this application of the constant symbol to the lambda abstraction over the body of I. That is a standard way. I don't dive here into that, so that we can avoid another binding mechanism in this framework where we already have lambda abstraction as a binder. But this is relevant for my talk because I reuse that all over the place on the next slide. Okay, so that is a bit technical here, but it's a very elegant, simple language actually that now introduces you a logic. Of course, you can now introduce further logical connectives in the obvious way. You can define them based on the others. By the way, Church and Peter Andrews have shown, and Henkin and so on, that you can also start out just with equality as a primitive logical symbol and then define all the others from them, also quantification, for example. Okay, so there would have been an alternative choice here. Hol is a language of terms, and terms of type O are the terms that actually are called formulas. So now let me show you how I embed Hol in Hol, and then Hol again in this embedding, and so on. Hol formulas of the lowest layer, I have already mentioned that, are those terms that have and carry type O, Boolean type. At the next layer, we explore now an interesting observation, namely that if you look at the predicate type from I to O, then you can find on that level of that predicate type, again, a Boolean algebra, which you can exploit to formulate higher order logic on that level. So we introduce a new Boolean type in the embedded logic and consider now terms of type I to O as our new formulas on that layer. So it's a real fragment of the language. It's now the terms of type I to O, which are giving us the formulas on the next layer. And on the next layer, we consider, reiterate that trick, and we consider predicates from I to that O prime Boolean type on the first layer, and so on. You can iterate the process now arbitrarily. So how do the definitions now look like? Here's the Isabel Hol system where I've formally carried out this experiment. And I introduce now here in the first 4 lines, this is essentially all you need, the new connectives on the second layer, including then a validity notion, so that other connectives can be defined, which you see here. So what do we see here on that layer? So you see that I introduce here a negation symbol. The ASCII representation is E1 not, and I can give that in the surface a nicer LaTeX-like representation, the negation symbol, and I give it this superscript 1 for indicating that I'm now on Hol level 1, which I define in terms of the lambda terms here on right, which are at the 0 level. So these are lambda terms in my base meta logic Hol. And you see I introduced that just as abbreviations for the terms. Basically what I'm saying is negation can be associated with a set complement on that predicate level, so on the Boolean type level that I have introduced. And negation can be associated with set union and so on. This is what I'm exploiting, and this trick also works for this pi operator. Also, that can be lifted. I can't go into the details, but it's an obvious definition here. So this logical connectives at the embedded first layer are just abbreviations for these terms. This is just what I have, and I use now compositionality and beta reduction in the system to work with them. For example, I can introduce now also new connectives via this idea of defining them based on the others, and then I can carry out experiments in order, very important, sorry, there I have to step back. I introduce a validity statement that simply does the obvious thing, which you know from forcing and from forcing context in modal logic, for example, where you say the validity of one of these formulas at the lifted layer is given when for all of these elements of type I, the property holds. So it just checks for universal validity for all of the objects of type I. So that is exactly what is written here. And that is also exactly the notion that modal logic does when it says, well, a modal logic formula is valid if it holds for all worlds. So you can associate in that reading the type I with a notion of possible worlds, and then you have here true sets of possible worlds at the predicate level represented, and you say such an formula is valid whether this true set of possible worlds is the full set. Exactly these ideas are captured by this notion of validity. So very important, no axiom. just abbreviations, I find a representation of classical higher order logic in higher order logic itself at that higher type level. And now, modulo this notion of validity, I prove that the axioms of higher order logic, as for instance published by Church, Andrews, and so on, prominent figures, can be validated. So I prove them automatically in Isabelle Holl. You see here that command plus that calls a tableau prover in more or less no time, and you get a validation of these statements. So the axioms 1 to 6, and also functional and Boolean extensionality. Only with Boolean extensionality, I have this additional assumption here that I have just type I being of a single element. But you see, starting from these abbreviations, I can find the patterns of higher order logic and validate the patterns of higher order logic at that layer. And I can even perform now, of course, statements of completeness and soundness relative to my starting point layer, like I show here. So for instance, you can do an absolute consistency statement saying at the meta level, I say there exists a formula phi, so that phi is not valid at the object level one. So there is a formula phi which is not true. I mean, if I had explosion, everything was true. So that is exploiting actually here this notion and says there is no explosion. And you can also formulate other notions of consistency. This one here with respect to negation, there doesn't exist a phi that is valid in the embedded layer and not valid in the embedded layer. Or you can call a model finder at the abstract level and just tell it, give me a model of that, what I have formalized here. Well, that's trivial because I don't even have a single axiom here. There's of course a trivial model, right? So now I can iterate that process. And I can do the same trick again. Now I start and formulate at the next level an embedding of, so that is now Holl level 2 in Holl level 1. And you see, I actually copy just these kind of definitions and formulate now new logical connectives, superscript 2, and they are just abbreviations for these lambda terms living at the level 1. And again, I introduce my further connectives. And again, I can do now experiments. I can do now experiments that you can interpret as following. At the meta level, I can see and prove that at the first level, it's valid that at the next layer, the second layer, I have modus ponens. Or here, the consistency statement. At the meta level, I can show that at the embedded level 1, there exists a formula phi such that at level 2, I don't have explosion, and so on. So that process can be iterated. So you see, what I get here is a very natural isomorphism between the meta level and layers of embedded layers of logic, which essentially all have the same structure. And I can use now this kind of reflection principles to reason about the properties of the embedded layers. And that, of course, works now also if I change the logic context. So we have done that in several papers where we exploited that. I pointed to that. So you can do richer logics and embed presumably richer logics in classical higher order logic and reason about their structure in that meta logic. So I could switch and show you all what I have shown you here in an online demo and show also how performant the reasoners are meanwhile to carry out such studies. But let me rather give time for discussion and come to a few statements here that eventually lead to questions. So the presented work is an interesting, for me interesting at least, input to reflect on notions of logical consciousness in a way, and to think about how I can eventually prove by reflection that reasoning systems are sound, complete, and also consistent. Of course, absolute consistency at the meta level, that's out of question because we have Gödel's result there. But you see here that eventually Gödel's result, my third bullet point, are often interpreted way too restrictive in many contexts actually. And for me, an interesting question is, well, this particular elegance that Church's type theory brings in the picture here by using the compositionality that is essential for what I've shown you of the lambda calculus, is that an important ingredient in the given context here? And I have pointed out, so what I've shown you, that does not just work for higher order logic and higher order logic. You can now reason about many other logic formalisms in that way. And that, of course, leads to the question whether we can eventually one day build AI systems that can, given arguments or pattern in the real world, discover on their own logics that actually work for this given patterns, for this argumentation structure in a paper, for arguments you find in a legal court. And then you could eventually ask an AI system, what is the logic that fits with these kind of argumentation patterns we have here? Or is there none? Do we have definitely conflicting, rhetorically overloaded argument that does not have a logical interpretation? Well, but this is future research to set up an experiment like that. And here I only have now, yeah, that's all I can say. Thank you for listening.